Hello students, good evening. Welcome to GATE Wallah. My name is 𝐂𝐚𝐿. I am having 15 years of experience as GATE faculty. I am faculty of Computer Science branch. I am going to teach here Theory of Computation and Compiler Design subjects. In today's session, I am going to discuss about Theory of Computation subject. Before going to start the subject, Theory of Computation, let me congratulate all the students who secured good ranks in the GATE examination, GATE 2024. Right. So in this lecture series, I am going to discuss about the subject Theory of Computation. Every day we are going to meet at live at 8 p.m. In this lecture series, I am going to discuss about basics to in-depth knowledge which is required to solve GATE questions. Our focus is mainly on GATE 2025. Before going to start, students, please give me clarity on whether my voice is audible or not. If I get the confirmation, I will proceed to discuss about this subject. So our today's topic is Theory of Computation for GATE 2025 point of view. So this is a GATE lecture series on Theory of Computation. In this, we are discussing all the topics related to GATE examination point of view. So what I am showing some diagram here. This is the overall overview of the syllabus that we are going to discuss. Right. So Theory of Computation, subject having mainly 4 concepts: regular, context free, context sensitive, recursive enumerable. If you see the automata point of view, finite automata, push-down automata, linear bounded automata, Turing machine. So in Theory of Computation, we are discussing about 4 topics, 4 languages, 4 automata. Namely, it is very clear here. We are discussing mainly 4 topics. First topic, finite automata and regular languages. Second one, push-down automata and context-free languages. Third one, Turing machine and recursive enumerable languages. Fourth one, undecidability. So these are the topics mainly we are going to discuss in our first class to last class. Most of the questions, if you see in the GATE examination, will get from these topics. I will show you the weightages also, how we will get the weightage. Right. So what is the subject actually? How this subject is important for GATE examination point of view? What advantage you will get from this subject while writing the GATE exam? See, the subject Theory of Computation is one of the high weightage subject in our branch of computer science. High weightage means we will get a good number of marks. Generally, we will get 7 to 10 marks from this subject. 7 marks to 10 marks. 7 to 10 means that is one of the very important subject in GATE point of view. This is a high weightage subject. Theory of why, what is the importance of this subject? Theory of computation for GATE students is, this is high weightage subject. The next one is, this is highly scoring subject. Means if you read this subject properly, if you understand all the concepts properly, we are going to assume we get 10 marks. You are going to get all the 10 marks as it is. So there is no much difficulties here. There are tricky questions, definitely we'll get in the GATE papers. But if you study properly, we can solve all those questions once you understand my classes. So in our classes, we are going to discuss from basics to GATE level. After listening all these classes, definitely you will solve all the GATE questions. In today's session also, we are going to discuss some of the GATE questions after discussing few concepts. Right. So this is the importance of this subject. One more importance is theory of computation and compiler design. Compiler design is the other subject. So that is interrelated with this subject, theory of computation. So if you have a good knowledge of theory of computation, compiler design becomes very, very easy. All these two subjects together, we can expect 15 to 20 marks. A max of 20 marks, minimum of 15 marks. So these two subjects are almost seems to be same. To understand this subject compiler design, this is the base. So study theory of computation carefully and properly, then understanding compiler design becomes very much easy for you. Right. So here in GATE Wallah, I am going to discuss these two subjects, theory of computation and compiler design. Right. In today's session, our focus is on only theory of computation. So these are the topics we are going to discuss in the subject theory of computation. So we have 4 topics here. Actually, there is one more topic here in the previous slide. If you see, context sensitive languages and LBA, we don't get questions from this part. That's why in the GATE syllabus, if you see, we don't have this in a GATE syllabus. So we are focusing on these topics only. We have only 3 automata for examination point of view, and we have 3 languages. So our concentration is on 3 automata and 3 languages. Right. So in these 4 concepts, these are the concepts as per the GATE syllabus. Out of these 4 concepts, in GATE papers, if you observe, 50% of the questions will get from the first topic itself. First topic is the high weightage topic. So in the subject theory of computation, 50% of the questions we are getting from first topic. So 20%, most of the times like this, but sometimes it may varies. 20%. While studying also, our time will be focused based on this. We are dedicating our time on these topics based on these percentages. So remaining 30% weightage is for these 2 topics. So this is the way. So whenever you are studying theory of computation, study carefully and properly first topic, because first topic is very important one. We are going to get good number of questions from the first topic, and all these concepts are interrelated. So if you know the finite automata concepts properly, understanding push-down automata Turing equation also becomes very easy. So this is about importance of this subject. This is a high weightage subject, first one, then a highly scoring subject. Then if you study this subject, understanding compiler design is also easy. So these are the main advantages of this subject theory of computation. And the topics, if you observe what we are going to study in our lecture series for GATE examination point of view, these are the topics and these are the weightages of these topics. 50% weightage for the first topic, 20% for the second topic, third and fourth topics, 30% weightage. Right. So this is about just overview of this topic, theory of computation. Okay students, so with this introduction I can start directly our subject, theory of computation. I am going to see the definition. Let us study the definition first, then all other possibilities. I think up to this everything is clear. Till now I explained only importance of the subject, how we can use the subject to crack GATE exam, how it is useful for GATE students of computer science. Right. So let us start studying this subject. Theory of computation. First let me start from name of the subject itself. The subject theory of computation having different names. If you see the books, the name of the subject is theory of computation is written on some books. Theory of computer science written on some books, and the name of the subject is written like this also, formal language and automata theory. Like this there are different names. So let us see why these many names are there for the subject and what is the use of the subject for computer science students, for our branch of computer science. See, there is a definition here. Theory of computation, the general definitions, if you observe from the books, the definitions are like this. So the first definition, let us concentrate on the first definition. Once we understand this, then we will go for the second definition. Theory of computation means it is the mathematical study of computing machines and their capabilities. Mathematical study of computing machines and their capabilities. The definition is very much clear. We have only two terminologies. Theory of computation is nothing but mathematical study of computing machines. Let me elaborate this definition. What is the meaning of this? So here they are saying that theory of computation is mathematical study of computing machines. Mathematical study of computing machines means what we are going to study in this. What type of mathematical study we are studying here on computing machines. We know the meaning of computing machines. If you understand the meaning of mathematical study, the definition is very much clear. Hello students, welcome. So some new students are joining. For them I am introducing this. This is our subject, theory of computation, in our today's discussion for GATE examination point of view. For GATE 2025. Right. So I am starting from the basics here. So theory of computation is nothing but it is the mathematical study of computing machines. What is this mathematical study? See, by using computing machines, every problem is not solvable. By using our computers, all the real world problems are not solvable. We can able to solve few problems by using computers. We cannot solve some problems by using computers. So by using the subject, by using some techniques, we can categorize what are the problems solvable by computers, what are the problems not solvable by computers. So this is the major advantage of this subject. So if the problem is not solvable, program cannot be written for that, algorithm cannot be written for that. We cannot solve those problems by computers. If the problem is solvable, then program is possible, algorithm is possible. So first of all, the problem is solvable problem by computers or not solvable by problem by computers, that we have to study. For this we have different techniques in this subject. So by using those techniques, So we will categorize the problems into mainly two categories. So names, generally the names are decidable problems and decidable problems. So decidable problems are the problems we can solve by computers. Undecidable problems are the problems computers cannot solve those. Like this, the problems are categorized into two categories. So there are some problems which are decidable, there are some problems which are undecidable. Decidable problems generally defined as the problems for which algorithm exist. The problems for which algorithm exist. Undecidable problems means problem for which algorithm not exist. If algorithm exists for which we can construct a program, algorithm exists for which we can construct a program, it is solvable by computers. If algorithm not exist, then program is not possible, algorithm is not possible, those comes under undecidable problems. So algorithm exists, decidable problem, algorithm not exist, undecidable problem. Let us see some examples. What type of problems are decidable? All the problems that we are studying in our algorithms, sorting problems, searching problems, all this list comes under decidable problems. Undecidable problem for which we can construct programs, we can write programs, algorithms also exist. Undecidable problems, unsolvable problems, computers cannot solve this. These problems are ambiguity problem. Ambiguity problem. We have post correspondence problem, generally called as PCP. I'm just giving the name like this. There are so many number of problems, n number of problems which are unsolvable problems. Like this, whenever you see the problems list, the problems list generally categorized into two things. One is a decidable problem, undecidable problem. Decidable problems means problems solved by computers. Undecidable problems means problems not solvable by computers. Like this, we have to categorize the list of the problems. On what basis we are doing this? For this, we have certain techniques. All those techniques are based on some mathematics. So this mathematical study of computers we are going to discuss in this subject. So the meaning of theory of computation is nothing but mathematical study of computing machines and their capabilities. Computing machine capability also we are going to study here. That means what a computers can do, what a computers cannot do, all these things we are going to discuss here. So this is overall view of this subject, the overview of this subject, how this subject is useful for our branch of computers. Right. So our main concept of studying this subject is, application of this subject is to, that's why every year in a GATE paper, if you observe, there is one question: which problems are decidable, which problems are undecidable, which problems are solvable by computers, which problems are not solvable by computer. This is a common question every GATE. If you want to solve those type of questions, this subject is compulsory. So to have the knowledge of those kind of concepts, here we are studying automata theory and formal languages. So theory of computation, other definition, we have another definition. The name of the definition is, it is a study of automata theory and formal languages. So these two definitions seems clear. Mathematical study of computing machines capabilities we are studying, that is one definition. Other definition is automata theory and formal language. These mathematical techniques are called as automata theory and formal language. Those we are going to study. That's why if you see the syllabus, in these mathematical techniques we are mainly studying about two things: automata, formal languages. Here we are discussing about three types of automata: finite automata, push down automata, Turing machine or Turing automata. Automata machine, same meaning. Finite automata, push down automata, Turing machine. These are the automata we are studying here. And three languages: regular languages, context free languages, recursive enumerable languages. So this is the overview what we are going to study in our course. In this theory of computation course, these are the topics we are going to study from basics to gate point of view, gate level. Okay, right. So this is about overview of this subject. So to understand this, so many mathematical things are involved here. That's why let me explain some of the terminologies. After that, directly I'll go and discuss about this first topic, finite automata, in today's session. So let us start studying some of the terminologies. If anybody having any, if you want to ask any questions, whatever is completed till now, you can ask me. Somebody is saying always fear of undecidability. Don't worry, I am there here. I can give you different type of tricks, different techniques to solve decidability and undecidability questions in a easy way, especially gate questions. So till now what we studied, what is the subject? What is the subject theory of computation? How it is useful for gate? How it is useful for computer science? So for computer science, the main application of the subject is which problems are solvable, which problems are not solvable, which problems are decidable, which problems are undecidable. That's why that is the last topic. So by studying all the previous basics, previous automata, the automata of DFA, finite automata, push down automata, Turing machines, based on this knowledge, so decidability and undecidability concepts we will study. Right. We are studying from basics. In today's class, I'll discuss some of the basic terminologies which are required to understand this subject, and then some basic definitions and basic automata of finite automata nature. So let us start studying some of the terminologies here. Alphabet. Without knowledge of these terminologies, it is difficult to understand this subject. That's why first let us try to understand what is the meaning of alphabet. Alphabet, the definition is clearly written here: finite, non-empty set of symbols. So alphabet is nothing but simply set of symbols. Alphabet is set of symbols. The set nature is finite, non-empty. So any set of symbols we can call it as alphabet. So in the coming classes we'll get questions like this: construct DFA over this alphabet, construct push down automata over this alphabet. Then you should have the knowledge of alphabet. So what do you mean by alphabet? That's why we are studying here. Throughout our subject we can use this terminology. Set of symbols. So this is first one is a valid alphabet or not. We have two symbols here, valid alphabet. Second one is alphabet or not, A, 1, 2. Any set of symbols, alphabet. Third one, is it alphabet? Alphabets should be finite and non-empty. It is empty here. This is not an alphabet. I am writing something here. Is it alphabet? Hindi letters. Set of symbols. The symbols can be anything. Any symbols, not a problem. This is also alphabet. So here it is a mathematical concepts. All whatever we are discussing here, these are mathematical concepts. So your symbols can be anything. That is not a problem. It is a valid alphabet. Right. Like this, any set of symbols is called as alphabet. Then we go for alphabet is always represented with a symbol called as sigma. So whenever we are observing sigma, sigma is the representation of alphabet. Alphabet means set of symbols. Right. Then we will go and discuss about the terminology string. What do you mean by string here? Finite sequence of symbols over the given alphabet. Now you should not get any doubt what is alphabet. We already studied that. So alphabet is set of symbols. Set of symbols, what are the symbols present in the alphabet? Their sequence. Assume if my alphabet is AB. AB. This is sigma. Over this, generally strings will be like this. AB is one string. AB is one string. This symbol sequence, repetition of the symbols any number of times. All these are valid strings. This is also a string, this is also a string, this is also a string. Like this we have, this is 2 length, 4 length, 6 length. We have a 0 length string that is called as epsilon. Epsilon is 0 length string. Right. So this is string. Alphabet, set of symbols, symbols repetition is string. Next we have a terminology language. This is very important. What do you mean by language? Any set of strings. Any set of strings over the given alphabet. So if the alphabet is these symbols, over these symbols, set of strings. Strings collection, strings set, that is language. So here the language of C language, C, C++, Java, those are different. This is mathematical representations. So here our language represents in this way. In theory of computation, language is nothing but simply set of strings. Right. So I am writing some of the language here. Which is valid, which is not valid. Let us try to understand. Language set of strings over the given alphabet. So first one, L1. Is it a language? We have 3 strings here. Any set of strings is a language. This is valid language. In the first language we have finite number of strings. No problem. Set of strings is a language. It is valid. What about second one, L2? We have a strings, but number of strings are infinite. No problem. If the number of strings finite, then also language. Number of strings are infinite, then also language. That's why the definition clearly saying any set. The set can be finite, set can be infinite, set can be anything. So any number of strings is language. So second one is also valid language. See the third language, it seems to be something new. There is a set but no strings in that. Epsilon is yes, 0 length string. Epsilon is 0 length string. Right. What about third one, L3? If there is no string, then it comes under a valid language. Is it a valid language? It is empty set, okay. Is it comes under a valid language? Can we say it is a language? Yes, any set. So the definition is any set. Definition is any set. Any set. Set can be empty. That is also language. So in a language, number of strings can be 0, 1, 2, finite, infinite, anything. Based on the nature of the language, based on the number of strings of the language, some names are given here. If the language is of L3 type, this is called as empty language. Empty language. If the language is of finite nature, finite number of strings, this is called as finite language. If the language is L2, number of strings are infinite, this is called as infinite language. So like this, any set of strings, language is nothing but set of strings. That set can be anything. Set can be empty set, set can be finite set, set can be infinite set. Whatever it is a language. But based on the number of the strings in the language, languages are categorized as empty language, finite language, infinite language. Right. So first one comes under finite number of strings are there in L1, finite language. Infinite number of strings are there in L2, infinite language. Number of strings are empty, no problem, that is also language, because the definition is any set, that is comes under empty language. Okay, very good. Is it a fourth one is L4? Is it a valid language then? Observe the definition. See, the subject theory of computation is like this. We'll take the definition, we'll try to analyze. We'll get questions in the GATE examination from analysis part. Just reading definitions is not sufficient here. We need to analyze. We need to analyze the definitions. Most of the times we are getting questions once your concepts are very much clear. For that reason, we are doing analysis on every definition. See the L4 here. Number, how many strings are there in L4? Number of strings are 1. So this is a valid language. Most of the students will confuse. Epsilon is 0 length string. So number of strings in L4 is 0, like that students may think, but that is wrong way of thinking. Number of strings present in L4. There is one string present in L4. The string name can be empty, but string is there. So this comes under finite language. L5, number of strings present in L5 is 1. So this is also finite language. Just time right. L6, name of the language of L6 is, it is infinite language. Infinite language. L5 is also, L6 is also called as complete language. All strings are there here, so it is called as complete language. Complete language means the language in which all possible strings over the given alphabet exist. If we give any alphabet, sigma as AB, over this A comma B, all possible strings. See, all 0 length strings exist, all 1 length strings exist, all 2 length exist. All strings exist in any language, that is comes under where that is comes under complete language. Right. So this is about language. Why I am explaining all these different names to the languages? In the automata construction time, all possible strings is complete language. Yes, if any language contain all possible strings over the given alphabet, that language comes under complete language. Because in some questions they will ask this way, construct DFA for complete language. They don't mention the number of strings. Construct DFA for complete language. Then you should know what is complete language. For that reason I am explaining these basics. Sometimes they'll ask construct DFA for empty language. These are the previous gate questions. These type of questions are there in previous papers. So by keeping all these questions in mind, my flow of subject, sequence of subject is going in this way. Sometimes what is the language accepted by this DFA? Finite language, empty language, complete language, this way they'll ask. So if you want to answer these type of questions, first you should know what is the meaning of finite language, what is the meaning of empty language, what is the meaning of complete language. If you know this clearly, then only you can understand, you can able to answer those type of questions. Okay students, till now we concentrate on terminologies. What is the alphabet, what is the string, what is the language, and what is the meaning of empty language, what is the meaning of complete language, what is the meaning of finite language, all these different things. So with these basics, I think it is clear. If anybody having doubts, you can ask your questions in the chat. So this is the language, string, alphabet. Alphabet is nothing but simply set of symbols. Symbol sequence is string, strings collection or set of strings is language, and the language names are like this. So with this basics, we can comfortably enter into our first automata, very important one. Symbol is nothing but sequence of, a symbol can be anything. You can use English language symbols, alphabets, any alphabet. So let us start our first one, finite automata. In our tomorrow discussion is mostly on finite automata. So we are going to start this topic, finite automata. It is one of the very important concepts in theory of computation. Most of the times 50% of the questions of gate paper will get from this topic, finite automata and its language, regular language. These two topics, finite automata and regular language, are very important. Regular language is also interrelated concept of finite automata. If you understand finite automata, regular language is very easy. So that topic we are going to discuss now. Are you ready, students? Shall we start this? Finite automata. This total subject theory of computation is automata, languages. So we are discussing different automata and discussing different languages. So don't confuse about these terminologies. Automata is nothing but machine. Languages are like our C, C++. These are mathematical notations. Automata and languages are mathematical notations. Right. So today our discussion is on finite automata. So what is this finite automata? See the definition. Finite automata is a mathematical model. not only this finite automata, throughout this subject theory of computation, whenever we are going to study definition of any automata, push down automata, the first sentence is like this: push down automata is a mathematical model. Turing machine is a mathematical model. Total theory of computation subject is a mathematical model. So like this, every definition starts like this only. It is a mathematical model which contains finite number of states and transitions. So the nature of this automata, finite automata, is it is having finite number of states. I will show you how this automata looks like. This is one of the finite automata having states, transitions. States are generally circles, transitions are arrows in between states. Why this finite automata generally used? In order to represent some of the practical situations. If you want to design any practical situation in computer science, to study the practical situations of our computer science, we'll use some diagrams. Those diagrams generally called as mathematical study, or they are also called as automata. So these are called as transition diagrams. Mathematical models, those models, yes, machine, that is automata, both are same. So these mathematical models we are studying with the help of automata. That automata is called as machine. So somebody asking, sir, it is not DFA, it is not NFA. Where I mentioned example of DFA. Okay. Let me come to this, because still now we have not studied the definition of DFA. So once we study, then you come to know whether it is DFA or not. Whether it is DFA or NFA will come for that. Example of finite automata. I am showing this is not for the example of DFA, example of finite automata. This is a valid finite automata. Whether it is DFA, whether it is NFA, we are going to study that. This is also one of the finite automata. Finite states, transitions. So finite automata looks in this way. All these are, forget about this, examples of DFA. So all these are examples of finite automata. Right. Finite automata is a mathematical model which is generally used to represent the practical situations of our computer science. The nature of this automata is finite number of states are there, that's why the name finite automata. Where this is used in practical situations, we will use in design of compilers. These concepts we can see how these will be used in compiler design. So we have mainly two types of finite automata: without output finite automata and with output finite automata. In the without output automata, we have three techniques. Without output, three techniques. With output, two techniques. Studying about these 5 techniques is our topic. You come to know how this DFA, NFA, epsilon NFA exactly looks like in the coming classes. We'll see where how this will be. That's why I told you compiler design, theory of computation are interlinked concepts. Theory of computation concepts directly used in compiler design to design some of the phases. So in which phase, which topic, that is also one of the gate question. So in the coming classes we are going to study that. But here finite automata practical application is, it is used in compilers. So we are studying means in computer science somewhere we are using it. Where we are using is compiler design subject. Melee more machine is in the circuit design. Circuit design. So you come to know while studying these topics how you are going to use this in those topics that we'll study. Right. So today our discussion is on finite automata. So in finite automata, what we have to study is learning about construction techniques of these 5 things. How to construct DFA, what is DFA, how to construct NFA, how to construct epsilon NFA, how to construct Mealy machine, how to construct Moore machine. So studying about these 5 techniques, is study of finite automata. So in today's session, we are going to start our discussion from first one, deterministic finite automata. Deterministic finite automata, also known as DFA. Finite automata means studying about 5 techniques. So in that, let us start studying from the first technique, that is deterministic finite automata, DFA. Right. So this is what we have to study in this deterministic finite automata. First, what is deterministic finite automata? What is DFA? Which automata is DFA, which is not a DFA? Next one is minimizing the DFA, reducing the states of the DFA, because every DFA is not minimal, we need to reduce the states. Next, if a DFA is given, how to identify the language. Next, if a language is given, how to construct the DFA. So these are the topics mainly we are discussing in this deterministic finite automata concept. In that first one is recognizing which automata is DFA, which is not a DFA. So this is our today's discussion. So first let us see the definition. Right. Is it clear up to now? Is it clear? So way of discussion, am I fast, or any suggestions? If you want to say anything, you can interact with me in the chat. Right. So we are going to start our discussion from the first topic, finite automata, in that subtopic deterministic finite automata. Right. Slow hai aur badhayenge. If some basics completed, then we can solve the questions in a faster way. So definition, deterministic finite automata definition. It is a finite automata in which from every state on every input symbol exactly one definition should exist, exactly one transition should exist. In this topic deterministic finite automata, this definition is very important, because now we are going to see some questions. So the moment you see any automata, you have to recognize whether it is DFA or not. For that, this definition helps a lot. It is a finite automata. Deterministic finite automata means it is a finite automata in which from every state on every input symbol exactly one transition should exist. So recognizing which is a DFA, which is not a DFA is very, very important thing. For that, the definition is saying on every state, on every input symbol, on every state, on every input, exactly one transition. That is the main thing, exactly one transition. More than one also not allowed, less than one also not allowed. If any automata satisfies for that, yes, from every state, for every symbol, one transition exists, that comes under DFA. We can confidently say that automata DFA. Now in today's session, we will see which type of automata comes under DFA, which type of automata not comes under DFA. Why? Because why this is that much important is our next concepts, if you want to move further to the next concepts, like minimization of DFA, to apply minimization concepts on automata, it should be DFA. So we have to detect if the automata is DFA, then only minimization is possible. Next, if you want to complement, then automata is DFA, then only we can complement. Like this, there are so many applications, so many algorithms. If you want to apply on an automata, it should be DFA. That's why a given automata is DFA or not, detection is very, very important. So the definition is like this. Based on this definition, we are going to recognize what type of automata comes under DFA, what is not a DFA. Now I am showing you some automata. Tell me whether it is comes under DFA or not. Right. This is the automata. So what is the definition of DFA? From every state on every symbol transition exists, then only DFA. What are the symbols here? Our input alphabet sigma is nothing but A comma B. So to say anything is DFA, here circles are states. Circles are states. This is called as diagram representation of finite automata. In this, we have circles named as states. We have transitions, edges named as transitions. There is always one initial state for every automata, like this arrow, initial arrow, that is initial state. Double circle things are called as final states. This is just introduction. Right. So this is the automata. I am saying it is automata. To say it is DFA, there are conditions. What are those conditions? On every state, on every symbol, edges exist, then DFA. That means from every state, on every symbol, transition exists, then only DFA. Let us apply this definition on this automata. From Q0 on A, transition exists. No, so this is okay. From Q0 on B, transition exists. So Q0 state clearly satisfying our definition, so there is no problem here. Check similar thing on Q1. Q1 on B, transition exists. Q1 on A, state Q1 on symbol A, there is no transition. So A transition is missing here. That's why this is like this, it is missing here. This is not a DFA. It is not a DFA. So to say DFA, from every state or every symbol, transition should exist. If on any state, on any symbol, transition is missing, that means zero transitions. Q1 on A, number of transitions are zero. Zero transition, not a DFA. See the definition. Exactly one transition. Exactly one transition. Less than one, zero transition, not a DFA. More than one, not a DFA. Right. Let us see one more. Now this is it DFA? I have an initial state, I have a final state. This is part of this. Initial state is there here. There is no edge, initial to final. This type of automata comes under DFA. The question is, if automata looks like this, is it comes under DFA? Right. So you should have a clear understanding of our definition. Right. Let me show. I'll explain all this, but let me show one more automata. See here, there is the initial state, there is a final state, double circle one, final state, initial state, and initial to final not reachable. Starting from initial state, we cannot reach the final state. Such type of automata comes under DFA or not. Such type of finite automata comes under DFA or not. So based on our definition, we have to analyze all these kind of automata. which is comes under DFA, which is not comes under DFA. Let me show you one more. Okay, assume here I don't have a final state. This is also non-final state. Both are non-finals. Is it comes under DFA? This type of automata comes under DFA? Right. If you want to give answer for all these type of questions, we have to study this DFA concept in a more clear manner. So that is called as formal definition. To understand the concept of DFA in a more clear way, the DFA is defined like this. So previous one is the general definition, whatever we studied. From every state, every symbol transition should exist. That is the general definition. If you want to study in a more clear way, this is the best one. So if you want to say any automata as DFA, these 5 tuples should be there in that. These 5 things should be there. If 5 things are there, we can say confidently that automata is DFA. 5 things are not there, that is not a DFA. So what are these 5 things? First one, Q. Q sigma, Q0, F delta. To say any automata as DFA, 5 things should be there. Q, sigma, Q0, F delta. What is Q? Finite number of states. Finite set of states, finite number of states, okay. Sigma, input alphabet, finite number of input symbols. To say DFA, finite number of states, finite number of input symbols. Third one is, it's a 5 tuple one. Initial state. How many initial states possible in DFA? How many number of initial states possible? Initial state should always be 1. Only 1. This whatever Q0 is there, this is only 1 initial state. Only 1 initial state. How many final states possible in DFA? See the F here, set of final state. Set of final state. How many final states possible? How many number of final states allowed in DFA? Any number of final state, any, 1 or more, yes, because it is set, any number of final state. And transition function, the transition function defined as Q cross sigma gives Q, means this is our definition. Q is state, sigma gives Q. State, input goes to state. From every state on every symbol, 1 transition. This is what the meaning. So if any automata having these 5 things, that we can call it as DFA. So finite number of states, finite number of input symbols, only 1 initial state, any number of final states, transition function, that is from every state, every symbol, transition should exist. Now let us apply this on our previous example. This automata comes under DFA or not? There are no transitions here. There are no transitions between Q0 and Q1. If the automata looks in this way, is it comes under DFA or not? So apply with these 5 things. Whether all these 5 things exist in this automata or not, check it out. If exist, confidently call it as DFA, otherwise not. First Q, finite number of states. Yes, exist. Input alphabet, exist. 1 initial state, exist. F is set of final states, exist. Delta, transition function, Transition function is from every state, every input symbol, exactly one transition. So here from Q0 state on symbol A, transition exists. Q0 state on symbol B, transition exists. From every state on every symbol, transition exists. Q1 on symbol A, transition exists. Q1 on symbol B, transition exists. So from every state on every symbol, transition exists. Delta is also okay. So this automata satisfying our 5 tuple definition. All the 5 tuple clearly there in this automata. So it is a perfectly valid DFA. If you have any confusion on this definition, don't worry, apply this 5 tuple definition. If any automata satisfying the 5 tuple definition, confidently call it as a DFA. So this automata is satisfying. Some students may think like this. So this automata don't have initial to final edges. No problem. Then it will not comes under minimal DFA. It is a valid DFA. It is a valid DFA. May not be minimal DFA. For that reason, we are performing minimization of the DFA. That comes under other concept, but not on the DFA detection concept. So to say it is a valid DFA or not, we can confidently say this automata is a valid DFA. Let me give one more. Now see this automata. Now what is DFA? If you want to check any automata as DFA or not, the 5 tuple definition. Yeah, a language, whether it is accepting empty or non-empty, that way comes under later. The topic we'll study properly. So now we'll see one more. See this automata, nature of this automata. We have 2 states, Q0 state, Q1 state. There is no edge, there is no transition from initial to final. From initial state to final state, we don't have any transition. This type of automata comes under DFA or not. Is it DFA? Check it out. So here no confusion, just apply our formal definition concept, 5 tuple concept. Yes, here unreachable final state is there, okay, but is it DFA? Initially, just to give you understanding, this is a, assume it as finite automata. Whether it is DFA or not, we don't know. Apply our concept and find out whether it is comes under a DFA or not. DFA, okay. Apply 5 tuple. Finite number of states, yes. Finite number of input symbols, yes. 2 symbols, A, B. How many initial states? Only one. The concept of initial state also satisfies. How many number of final states? Final states can be anything. So Q1, one final state. What is this delta? Delta is our general definition. Every state, every input symbol transition exists or not, check it out. From Q0 on symbol A transition exists, on symbol B transition exists. From Q1 on symbol A transition exists, on symbol B transition exists. Delta also satisfies. So from every state, every symbol transition exists, delta satisfies. This automata is satisfying the 5 tuple definition. If any automata satisfies 5 tuple definition, confidently that is a DFA. This is clearly a DFA. So whether it is reachable, final state is reachable or not, we don't want. That is our further concepts. The language detections, minimization concepts, we don't want that one at this stage. So till now, we can say confidently this is one of the valid DFA. Let me design one automata. whether it is DFA or not. The question is whether it is DFA or not. If the automata is of this type, here what is the difference is there is no final state. We have initial state, there is no final state. Automata looks in this way, whether it is DFA or not. Very simple, whatever it may be, whatever the given question. So apply 5-tuple definition. Whether it is satisfying the 5-tuple definition or not. Check it out. Without final state, if without edge, DFA or not we verified. With final state, one final state, DFA or not we verified. Final state not reachable also we verified. Now if final states are not there, what happens? Then also no problem. Check it out. Finite number of states exist. Input alphabet exist. Initial state exist. Only one. What is F here? Set of final states. The set can be empty. Some people are saying one or more. It is not even one state also not necessary. One final state also not necessary to say DFA. Because the set can be empty set. The formal definition of DFA is saying F is set of final state. The set can be empty set. That's why number of final states can be 0. So 0 final states also valid. F also satisfies. Delta is transition function. What is the transition function? Every state on every input symbol transition exists or not. So for Q0 on A transition exists, on B transition exists. Q1 on A transition exists, on B transition exists. Transition function also clearly satisfying here. All the 5-tuple definition is satisfied by this automata. This automata is clearly a DFA. If the final state is not there, what happens? What happens? Just it will accept the empty language. Empty language also a valid language. So not an issue. That will accept the empty language. So if final state is not there, no issue. This automata is clearly DFA. Final state is there, not reachable, DFA. Final state not reachable, then also DFA. There is no edge, then also DFA. We don't want any confusion. Apply 5-tuple definition. Now let us focus on one more. Whether this automata comes under DFA or not. This automata comes under DFA or not. 5-tuple one. So finite number of states. Q is okay. Sigma is okay. Q0 one initial state is there. No problem. Set of final states. Till this one final state is there. That also satisfied. Delta. Every state, every symbol transition. But this automata violating the delta property, right? Q1, state Q1 on symbol B. We have one transition, one transition. From every state on every symbol, only one transition exists. Then DFA. But Q1 state on B, multiple transitions are there. So clearly it is not a DFA. It is not a DFA. I'm giving one somewhat bigger automata. Check it out whether this is DFA or not. Don't try to analyze the language now. Identify the language accepted by follow. This is not the question. Check whether this automata is DFA or not. There are so many states. So here 0, 1 transition. from this state? So check clearly. What is the transition function here? We have finite number of states, finite number of input symbol, 0, 1 input symbols, only one initial state. First one, this is the initial state, and this double circle one, this is the final state. 4 tuple are clear here, q, sigma, q0, f. These tuple are clear. Delta, whether it is clearly there or not there, we need to check. Transition function. What is transition function? Every state, every symbol, transition exists or not. So from initial state, 0, 1 exists, 0, 1 exists. Like this, if we check it out, come to this state here, I'll name it as k state, state number state number k, state number I, some states, state number f. Whether k state having delta property or not. That means every state, every symbol, transition exists or not. Easy one. So state, the state on 0 transition is missing, on 1 is there on. So if you have like this, then we can call it as DFA. Now all states, all transitions exist. If you don't have, not a DFA. So this is not a DFA. Now our next concepts, we have to see minimization of these things. We have to reduce the states of this. So these many states we have to reduce. If you want to do all this, it should be DFA. If you fail in checking DFA itself, those concepts becomes very difficult for us. So in our today's session, we studied what is DFA, how to recognize which automata comes under DFA. Okay students, so every day at 8 p.m. I am going to come live. So we are discussing concepts of DFA in a sequence manner, topic by topic, so gate point of view. So that's all about this session. Thank you. See you in our next session.